Hi all, this is the promised review about buffers and titration curves in order to help you complete your assignment for Biology 112 lab. Just a little review here from chapter 2. Remember that water molecules are considered to be polar molecules. So what does that mean? Well, remember that each water molecule is one oxygen covalently bonded to one hydrogen and then covalently bonded to a second hydrogen. And when we say that the oxygen and the hydrogen are covalently bonded, we mean that some of those electrons that reside in the valence shell of the oxygen, meaning they are the furthest away from the nucleus in that far area, they are shared between the nucleus of the oxygen and the nucleus of the hydrogen. So hydrogen is donating one of its electrons to be shared in this covalent bond, and oxygen is donating one of its valence electrons to be shared in that same covalent bond. So there are two electrons that are shared by this pair of atoms. And the same exact scenario goes to the other hydrogen sharing with oxygen. So the covalent bonds between the oxygen and the hydrogens are actually polar covalent bonds, which is a more specific type of a bond. And that is because oxygen by its nature is much more electronegative than the hydrogens. Remember what that means is just by its nature, just the way the universe made it, oxygen has a stronger pull for electrons toward itself than does hydrogen. So when they have established a relationship where they are sharing two electrons in between each other, those two electrons are closer to the oxygen's area than they are to the hydrogen. And that means that oxygen now has a little bit more negative charge around it than it did before it was involved in this relationship. So now there's a tiny bit more negative charge, just a fraction of one electron's worth, that is on this side of the molecule. And the hydrogens, their protons in the nucleus did not change, so they are slightly more positive than they were before this relationship. That means that the whole water molecule is polar. It acts like a weak little magnet, with one side of it being slightly tiny bit negative and one side of it being a tiny bit positive. Okay, so we call water a polar molecule. And what that means is that when ions, I've got a kitty cat here, when ions are placed into water, and in this case, do you see here, there's a clump of table salt, right, from your kitchen. When it's placed here in a beaker of water, the two ions, the sodium and the chloride, they dissociate, right? They come apart, and water molecules surround, not just in a circle, but in an actual sphere from every single direction. They surround each ion. In the case of a negative ion, like chloride, which has one more electrons, than protons, the positive sides of the water, the hydrogen sides of the water, are surrounding. They're like magnetically attracted to the negative chloride. And the positively charged sodium ion is surrounded by the negative sides of each water molecule. And so as everything in the liquid is kind of bouncing around, each of these ions has a water sphere bouncing around with it. Right? And so when we say that something's dissolved in water, like when table salt became dissolved in water, it means that the sodium and the chloride ions are separated from one another because there's a bunch of water in between. Okay? So let's see, how does that relate to what we're learning in this section of the course? Remember, what is an acid? An acid is any substance that when you place it into water or a watery solution, which we call aqueous solution, it will increase the number of free floating H pluses in that solution. Well, one example, what if instead of having sodium chloride, right, NaCl, which was the table salt I showed you in the previous slide, what if we had hydrochloric acid, which is HCl? So instead of being NaCl, it's HCl, but the relationship is the same. These are two ions, chloride, a negative ion, and hydrogen, a positive hydrogen ion, a positive ion. They're connected by an ionic bond, just like salt was in the previous example. And when you put them in water, they separate or dissociate from one another. Why did they separate and dissociate, which is like them dissolving? Well, because there's now a sphere of water molecules around this hydrogen ion, a sphere of water molecules around this chloride ion. And a base is something that is the opposite of that, is when it's a substance that when it's placed in water, it decreases the amount of free-floating protons or hydrogen ions in the solution. One way that it can do that is in this example, we again have sodium ion and this other ion called hydroxide, OH minus. When you put them into a watery environment, the sodium becomes surrounded by water, has a hydration shell around it, and this OH, you can't see it because my face is blocking it, but it says and it has a negative on it right there, right behind my little face. I didn't plan that perfectly. This will actually combine with whatever free-floating hydrogen H pluses are in the water and create H2O, right? So it grabbed H pluses to it and made them now no longer free-floating H pluses because now they're part of H2O, water molecule. So we have, by adding this component here to our solution, we have decreased the number of free-floating H pluses because we've collected them and added them to something. Okay? So that's a base. And remember that measuring pH is measuring the concentration of free-floating hydrogen ions in a solution at a logarithmic scale. So a pH number indicates, not directly, but it indirectly indicates how much H plus there was. So I've asked you these questions on quizzes and exams and in classes we're practicing. Okay, you have a mysterious substance and you add it to your beaker, and your beaker goes from being pH 7 to now being pH 7.5. What does that tell you about that mystery substance? Well, if you have added something to a solution and that solution is now more basic than it was before, in other words, more alkaline, higher pH, then it means that the thing you added to it was a base, right? The pH changed because you added acid or base, and you would see that indicated by different pH numbers. So last aspect of this review is, what is a buffer? A buffer is an aqueous solution, so again, watery solution, meaning water molecules with some dissolved other molecules in it. That makes it so when you add stuff to that aqueous solution that is an acid or a base, the pH does not change very much. So a buffer is something that resists changes in pH when acid or base are added to it. Just previous two slides, I told you that if you add something to an aqueous solution and becomes more acidic, that means you have added acid to it. And the same if you add base. Well, what if you add something to a solution and it does indeed become more acidic, and now you know that that thing you added is an acid? Now you take that acid and you add it to a solution that has buffer within it, then that solution is not going to change its pH, or not going to change the pH very much. So buffers are solutions, which again means water with specific molecules dissolved in it. It has specific molecules, these buffering molecules, that when acid is added, it still doesn't make it so that there is more free floating protons in there. Or when base is added, it doesn't mean that it now has less free floating protons in it. How is this possible? This is a graph that is from your lab manual. And what I want to point out on this graph is that it's basically showing the same type of an activity that you did. Okay, here is 0, meaning before anything was added, 0 things were added. You just have your beaker of solution. And you measured the pH of your starting solution, and that pH was, it looks like, maybe 7.5. And then you added 1 milliliter. Okay, 1 would be right here, milliliter added of acid, hydrochloric acid, right? When it falls into water, the H plus and Cl minus separate from one another, become both surrounded by water molecules, and yeah, they're now more free floating H plus or protons in there because these two ions came apart in water. So when you added that 1 milliliter of hydrochloric acid, notice that the pH is now went to like 2.5. And when you added a second milliliter of acid, pH is almost at 2, and by the time you added 4 milliliters of hydrochloric acid, your pH is at 4. And the thing is, the pH of the pure hydrochloric acid is 2. So by adding just 1 milliliter, or let's say 2 or 3 milliliters of hydrochloric acid, the pH to your whole beaker of solution, the whole beaker became the same pH as the hydrochloric acid itself. And then no matter how much you're adding, it's basically just the same because you are already at the pH of hydrochloric acid. And on the other hand, if you took your solution and you added 1 milliliter of a base, sodium hydroxide, a base, it immediately jumped to 11.5 or something, and eventually was 12, which is the pH of sodium hydroxide. This thing you were adding, that's the pH of it, is about 12. What this is showing us is a graph of a solution that has no buffer in it. This is probably just a beaker of water that you had. And when you add a little acid or a little base to that water, it immediately jumps to be almost the pH of the acid and base you've added. This here has no buffering capacity. This solution that we were working with has no buffer in it. This, on the other hand, looks different, right? So at 0, the pH was 7.5. But then when you added a milliliter of acid, notice how it did not jump very much. It did decrease a little tiny bit, but it did not jump. And then when you added more and more, it decreased but didn't jump. Eventually, it did have a very big change after you added that 4th milliliter of acid. It made a significant change in pH, and then eventually was again at the pH of hydrochloric acid, or nearing the pH of hydrochloric acid. Same exact situation was happening as you were adding 1 milliliter of base to this same solution. So from here, what we see is where it is flat-ish over here, that is the range where the buffer was working. Meaning, when you added a little acid or a little base, the pH changed only very little amount. So nearly horizontal line, but these at the end here do not count because they are actually not buffering. They're just the pH of the thing you're adding, right? It's like you're trying to add like a colored molecule to a beaker of water, and when the whole thing's already totally red, and then you add another drop of red, it just like doesn't change. It's just all red that it was before, right? The buffering here is like you're adding a drop of red dye and it's like not red at all, and then you add another drop of red dye and it's not red. In another milliliter and it's not red. And then another milliliter and all of a sudden, oh wow, it's like really red all of a sudden. That means that for a little while it was somehow like absorbing those added molecules, and so the color wasn't changing. In this case, it's not color changes, it's the pH changes. Okay, so there are two things we can glean from this buffer: is its buffering range and its buffering capacity. When we say buffering range, we mean between pH what and pH what is it maintaining about the same pH. So here where it's the most flat, so I would look at the y-axis, and here between 6.5 and maybe 8 or 8.25. 6.5 and maybe 8.5 is the buffering range of this buffer. So when you ask for buffering range, it's the pH range. So where on the y-axis is that flat area? The buffering capacity is where on the x-axis do you have that flatness. So if we have, this is kind of where it's mostly flat-ish. That is between 2 milliliters of base and about 2 or 3 milliliters of acid. So you would say that the buffering capacity for this particular buffer would be 2 milliliters of NaOH, the base, and 3 milliliters of hydrochloric acid. Okay, so your goal is to take your data that you collected in lab and make a graph like this one. Okay. In addition to making sure that you label the axis, right? On the x-axis should be the milliliters of acid and base added, just like it says here. And on the y-axis, which is your dependent variable, is the pH. Okay. The only other thing that you need to add to your assignment in order to get full credit is a figure legend. Figure legend is a really short, extremely concise and well-written paragraph or a couple of sentences that if someone was looking at your graph who has no idea what you were doing would have an understanding of what's going on. So here I can read mean population density of 2 species of Daphnia following artificial eutrophication of a small farm pond by application of organic fertilizer. 6 replicate 1 liter samples were drawn from 50 centimeter depth at 1100 hour each day. So they basically tell us a little bit of what they were doing, a little bit about the method or the process, one sentence, and then they told you the most important result that they can glean from it. And what you will have to tell me is a sentence that says titration curve of a mystery buffer, and then you tell me that has a buffering range such and such and buffering capacity such and such. And then you can say something like one sentence about how you performed the so-called experiment. Then you will read over your figure legend, which is this little paragraph, over and over until you're using the least amount of words to still clearly describe what is going on, and you're really precise in your grammar and your language. And of course, yours would say figure 1 because it's your first graph of the assignment. In this paper from which I took this graph, they had multiple graphs. So the first one was labeled figure 1, and the second one is labeled figure 2. Okay. I hope that was helpful, and there is a different document that gives you verbal instructions on how to graph in Microsoft Word in order to achieve what you're looking for. If you need the help, I'm sure there are many approaches to that, and I'm sharing one of them. Right? I'll see you in class.